5 seconds.
I'm frantically scribbling down notes. Tinker now.
In theory, we exist. Somebody, of course, needs to collapse the wave function and confirm our existence. And apparently, I have to give our chat software a kick. So I will do that. I don't know if it's going to work. Do you find Nightbot is super forgetful of...
Not on Twitch. I think it's a YouTube thing.
Yeah, literally every single time I have to re-log in, log out of Nightbot. So we're now live on the internet, but we haven't actually started the show. And then we'll start that in 5 minutes.
They see us.
They do see us. Yeah, so we definitely exist.
I'm not throwing Cheerios at you. This is the wrong show for that. So for those that are like, why do I hear a dog whining? My dog has been conditioned that when all the lights are on and I'm talking to my computer, that it's time to get Cheerios.
Is that because you're bribing your dog to keep quiet while you're trying to do your broadcast?
No. On Twitch, literally, whenever we get bits or subs when I'm streaming, I throw Cheerios at them because I have a whole separate dog cam.
Right.
But yeah, that's not a thing for Zoom.
Oh, listen to the dog. Where's the food?
Hold on. I'm gonna have to pick her up. There's no way we could do this.
I don't know why the Popo chat isn't working for me today. Okay. Well, I'm going to say hi to Andy Cowley, Astro B, Bob Moeller, Daniel McCool, David Fairweather, Ian Farquharan, Jorn Albert, Kevin Ayers, Larry Beckham, Miss Scooper, Nancy Graziano, Paranor, Rich Wilson, Arjone, Susan Hunter, Susie Murph, and Yuval Litvin. Hey, everyone. I have to look. I can't make the chat move to a place that's better for me right now. Like the screen just doesn't refresh. Anyway, YouTube, like what do you know? Computers aren't doing the things that we want them to do. What are the chances?
Iowa, are we?
Yeah, what are the chances of that happening? Cool. All right. So we got about another 2 minutes, and then we will start this up. And I'm gonna I'll make sure I've got the picture for the solar telescope. So have you figured out how to pronounce the name of the telescope?
You're asking me?
Yeah.
I think it's Inouye.
Yeah, Inouye.
It's named after Senator Inouye.
Right.
Senator Inouye. Okay. All right.
Yes,
good.
the late senator who died in 2012.
It's the same name as the airport, I think, on Maui. Yeah.
Possibly, he was quite a celebrity in Hawaii.
Yeah.
So it's Inouye.
Inouye.
Sorry.
Inouye.
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 Yeah. Yeah, we want to make sure we got that right.
Yeah.
I mean, I'm sure all the local Hawaiians are like, of course, we know the name, as you say, local celebrity. And for a lot of people, this telescope is just blowing, the pictures from this telescope are just blowing their minds.
Right. Would we be able to pull up the image?
Yep. Yeah. Well, I'll pull up the image while you're talking about it. So, and I will be able to share the image at you, and then you can sort of see what the audience is seeing while we're in that portion of the show.
Is the Inouye telescope up and running now?
Go ahead, Chris.
Its first light was back in December, and that's where they captured this image, but it doesn't go fully operational until the summer.
Yeah. They've got 3 more instruments, I think, to install on it before it's fully operational. Okay. We've reached the 5-minute mark, so I'm going to set all this up. And
Real quick. Hi, Flame Lord. That was all.
Okay.
My nephew's watching.
That's awesome. All right, here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, February 5th, 2020. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about James Webb might be delayed, a test that shows frame dragging, one of Einstein's predictions, the highest resolution photograph of the sun ever taken, and more, depending on how much time we have left. Joining me this week on my screen, we've got Annie Wilson. Annie.
Hello.
You're going to be muting back and forth, aren't you, as you're trying to manage an excited dog?
Yes, I am. The dog is used to getting treats when I stream, and yeah, she's very vocal about it.
Yeah. I think that's funny when you and Pamela, or when Pamela's doing the hangout-a-thon and the dogs were getting all kinds of treats based on various events that happened. Like those dogs were well trained. Also probably got sick by the end of that whole weekend, and now I'm sure it's anytime she goes anywhere near a computer or cameras get set up, they come a running.
Pretty much.
We've got Dr. Brian Koberlein. Brian.
Hi everybody. Good to be here.
Thank you for coming back. And we've got the new guy, Chris Carr. Chris, welcome to the Weekly Space Hangout.
Thank you, and I'm happy to be here.
So before we get into the rest of the show, tell us who you are.
Well, my name's Chris Carr. I am a first-year graduate student at Columbia Astronomy, that is, and I was recommended to the program by I think a mutual friend of ours, Moya McTeer, who was also a grad student. She was telling me about like this fun opportunity that she had to do this outreach show, and I asked, "Oh, could you like give my name to them as well?" And she actually did it. So I didn't think I'd get this far. So I'm happy. I'm happy that it worked out, and I'm glad to get back into the science outreach.
That's awesome. Yeah, no, it's good practice to just be sort of talking about science and explaining these concepts that you're working on, but to actually be able to explain these to the regular audience. And so I think the more scientists who get a chance to actually go through this process and have to learn to explain what it is that they're working on or what others are working on just helps as you do your research as well. So, and hopefully you'll definitely what is sort of some examples of some of the research that you're working on specifically?
I would say that I'm interested in anything that has to do with cosmology, so the study of the evolution of the universe as a whole, and the study of galaxies individually as well, because I think galaxy formation is another one of those fundamental questions a lot up there with like where did the Earth come from, or how did life come to be. I think galaxy formation is also one of those questions that I think deserves to be put on one of those pedestals.
Yeah.
And so that's really what drove me. That's really what drives my research now. And right now, I would say I mostly study the Milky Way because galactic astronomy is really in a time of renaissance. We have so much data from the Gaia missions, which is giving us the positions and the velocities of millions of stars in the Milky Way, combined with all these other spectroscopic surveys, which are telling us like reams of information about the chemistry of stars. And so it's really a great time to be a Milky Way astronomer, and I hope to take advantage of that in the coming years.
That's fantastic. Well, Chris, from everybody here, so glad that you joined us, and we will be talking with you more later as we talk about what is going to be one of the top stories of this entire year. So good timing. All right. So before we get on to this week's interview, I just want to take a second, of course, and thank our good friends at the Weekly Space Hangout crew. These are our executive producers. They're the ones who really help organize all of the shows that we do, all of the guests that we bring on, and we couldn't do this without them. So if you want to be a member of this incredible community, go to wshcrew.space. They will give you your executive producer instructions and then send you out to help organize more guests for the show. So, and of course, thanks to Nancy Graziano in particular for helping to do so much work behind the scenes. We could not do this without you, Nancy. All right, well, let's get on to the special guests this week. We've got Michael Werner and Peter Eisenhardt to talk about infrared astronomy. Welcome to the Weekly Space Hangout.
Thank you very much. It's nice to be here.
Hi, Fraser.
Well, the timing is absolutely terrific because all of the news about the loss of Spitzer just happened in the last couple of days. So it's a very bittersweet moment. So can you let people know who you are and what you do?
Yeah, my name is Michael Werner. I'm the project scientist for the Spitzer Space Telescope here at the Jet Propulsion Laboratory. I've been working on Spitzer for 43 years, so it's kind of my life's work.
Yeah. Thank you.
I'm Peter Eisenhardt. I've been working only for 33 years on Spitzer. I started working on it when it was still SIRTF. I've got my SIRTF shirt here. I don't know if you can see that.
Yep.
I joined Mike's team at NASA Ames in '87, and then he and I came to JPL when NASA decided it was time to get serious in 1990. But little did we know that getting serious means it would launch 13 years later in 2003. But in any case, it's now been Spitzer for as long as I've known it as SIRTF, and so I'm quite used to calling it Spitzer here, and happy to be talking about it. And as you say, it's a little bittersweet though with last week's news.
I mean, I am expecting that, of course, our audience is quite familiar with Spitzer and the rest of the great observatories, but I would love to sort of talk to you now that you've had a chance to see all of the work that Spitzer has done over the lifetime of its observations, and then look back at what your expectations were for the decades leading up to the design and construction and eventual launch of the mission. How did reality play out against your expectations?
Well, let me take a crack at that, and I'll pass it over to Peter in a second. We knew from the start, Spitzer's a cold telescope in space, which makes it very, very sensitive in the infrared because there's no infrared background radiation interfering with our observations. So Spitzer, even though it's only an 85 centimeter telescope, is as sensitive as a 10-meter telescope on the ground. And we knew for all these years what kept us going, that a big telescope like that with that sensitivity, instrumented with state-of-the-art detectors, would be tremendously powerful scientifically. But even so, we had no idea about the windows on the universe that would open. I'll mention one, which is the study of exoplanets. Peter can chime in perhaps in the study of distant galaxies, which is his expertise. At the time that we were designing Spitzer, we had very few exoplanets had been discovered, and we had no conception for what Spitzer would be able to do. Well, it turns out because of the fact that there are so many exoplanets that many of them are in orbits which are edge on as we see them, we can take advantage of that and study the exoplanet even though we never actually see it. If the exoplanet moves in front of the star, that's called the transit. The light from the star drops, and the amount of the drop tells us the size of the planet. Now, many telescopes can do that, but Spitzer is unusual because it's an infrared telescope. If the exoplanet goes behind the star, if we'd been seeing infrared radiation from Spitzer from the exoplanet up to that point, when it goes behind the star, the total infrared radiation from the system drops as well. And from that, we can infer the temperature of the exoplanet. We can infer from the details of what happens as it moves behind the star, information about its atmosphere, whether it has an atmosphere, how heat is transferred in the atmosphere, an amazing level of detail, again, about a planet that's never actually separately seen distinctly from the star. And the kind of ultimate case of that was the TRAPPIST-1 system, where we discovered or disambiguated 7 separate Earth-like planets, all within a small fraction of an astronomical unit of the same single faint red star. So Spitzer's studies of exoplanets and the detail which we've been able to infer is far beyond anything we could have imagined.
Wow.
I want to sort of amplify that a little bit. The very first astronomical paper I worked on, gosh, it was in the 70s, was on eclipsing binaries, and it was kind of a dull subject at that time. And I moved on, like Chris, I got excited about galaxy evolution formation, but I would never, in all these years of working on Spitzer until it actually started doing it, I would never have expected that eclipsing binary techniques would have the amazing impact on our understanding of the universe that they have, and that they would allow Spitzer to actually detect light from an exoplanet. And Spitzer's actually, as far as I understand, Mike, you can correct me, but I think Spitzer was the first telescope to directly detect light emitted by a planet around another star, which is phenomenal and not something we were thinking about at all. What we were thinking about, though, was distant galaxies. So let me say a couple words about that. And I'm going to cheat and show a few pictures from our book that Mike and I published last year. There it is. It's called More Things in the Heavens.
Yeah, I got a copy of it as well. So thank you so much for sending it. I haven't had a chance to dig into it yet, but I'm definitely excited to do so.
Well, we talk about pretty much everything in the universe, and so one of the basic things we know about the universe is that it's expanding. And here's a really nice graphic from WMAP. I don't know if you guys can see that, but anyway, you know, the universe is expanding. There was a big bang, and the universe has been expanding ever since, and actually it started accelerating. So what that means is that light from early on in the history of the universe has been expanding as well, and longer expanded wavelengths are redder. We see those as redder. The short wavelengths we see as blue, the long wavelengths we see as red, and the really long ones we call infrared. And so if we want to look back to early in the history of the universe, far, far away, we need to look at light that has been expanded into infrared wavelengths. And that's what Spitzer used as a big, big driver. And when I came to JPL in 1990, when Mike and I came in 1990, we thought maybe we could see galaxies where the expansion had been 500%. So wavelengths were 500% longer than they started. That would take them out nicely into the infrared. Well, what it turns out is that here's another sheet here, but from the book here, this is the most distant galaxy that we know of. This is a galaxy where the expansion is 1100%. It's at a redshift of 11. So those wavelengths are really shifted far out into the infrared, so far so that even Spitzer is starting to look into ultraviolet wavelengths. And I certainly would not have expected that. And so Spitzer's been successful in ways that we couldn't imagine because we weren't really thinking about exoplanets, and in ways that we might have imagined, but much more so than we would have ever had the audacity to predict.
Yeah. And so one of the things that's great about these kinds of telescopes, I mean, people sort of imagine that they're going to answer questions, but what they really do is just make you ask new questions. So for every question that you answer, you now have 10 new ones. So I would love to hear, sort of based on some of the incredible discoveries that you've seen from Spitzer, some of these observations, some of just these hints that you've gotten, especially things that were unexpected. What new questions now do you have in your mind that you would love to be able to say to maybe, come back around and have go into the thinking of some of the next generation telescopes that are in the works?
And in the area of exoplanets, the obvious question is, can we find planets which would be possibly habitable for life, which means liquid water on their surfaces, the way we think about it. A few of the TRAPPIST-1 planets have that characteristic. And then if we do the type of work that Peter talked about in the transits and the eclipses, the planet going in front of and behind the star, with a better instrument than we've had in the past, we can hope to look for the molecules in the atmospheres of these planets, which might conceivably be indicative of some biological processes going on.
Yeah.
So I think there's a whole set of questions about using observations of exoplanets to search for habitable and maybe even inhabited planets, or planets where life has got a toehold. which will be the grist for the mill of astronomers for decades. And Spitzer has pointed the way towards doing that type of work.
If I were to suggest a couple of things that one of the definitely surprising discoveries was that there are galaxies that seem to have formed much earlier on in the history of the universe. And so, we thought maybe we could see galaxies where their light had expanded 500% redshift 5. Instead, we're seeing galaxies where the light has expanded from redshift 11, much earlier in the history of the universe, only a few 100 million years after the Big Bang. And some of those galaxies seem already to be pretty far along in their development, even early in the history of the universe. And so it looks like maybe those galaxies formed much closer to the Big Bang than most astronomers thought was reasonable. And so that will be really a major topic for James Webb when it launches, hopefully next year. I guess you're going to say a little more.
Yeah, we'll be talking about that later on. Yeah, there's actually a story that just came out today, I think, about a galaxy that's been seen less than 2 billion years after the Big Bang that already had 300 billion masses of stars in it, and that it was already 1 billion years after the most of its star formation was complete. And so we're seeing that, in fact, the universe was in a much more advanced state than we would expect earlier on in its history. We kind of missed the party.
Well, yeah. So there's a popular analogy now in the field called we talk about cosmic dawn, which is when the first stars lit up and ionized hydrogen in the universe. After hydrogen went neutral following the Big Bang, it got ionized again by stars and maybe by quasars. That happened some hundreds of millions of years after the Big Bang. So that's cosmic dawn. There's cosmic high noon, which is about 3 or 4 billion years after the Big Bang, when star formation and quasar activity was really at its height. The universe was a much more happening place then, and even much more active then than it was at cosmic dawn. And then, well, nowadays it's cosmic dusk. Here we are.
Yeah.
So we haven't missed the entire party, but yeah, you can't get around that we're calling it cosmic dusk.
But even so, it's important to realize that in our galaxy, which is 13 billion years old, stars are forming even as we speak within a few hundred light years of the Earth. So we may have missed some of the action, but there's still an awful lot going on.
Well, and that's another region that Spitzer has just been absolutely pioneering in, is being able to peer through all of the gas and dust that cloaks these newly forming star systems to be able to reveal the conditions that are going on inside of them. I mean, our view to protoplanetary systems is really due to Spitzer in the last couple of decades. I mean, there's a lot more infrared now, but still, there's nothing else that's that cool and out in space, able to take those kinds of images.
That's right, and not only images, but also spectra. So if you imagine a disk of dust and gas around a star, as the star forms, a disk of dust and gas inevitably forms around it. And in that disk of dust and gas is where a planetary system is formed. If you look at our own solar system, you can see the planets all go around in the same direction. They roughly lie in the same plane. That's the fossil of the disk from which they formed. Spitzer has looked at these disks and studied their composition, studied the gaseous material within the terrestrial planet system or zone of that forming planetary system, finding water and other interesting molecules, or looking through the midplane of the disk in absorption at the central star and finding ices, again coated with water and other interesting molecules in the outer colder regions of these same disks. So Spitzer's done a census, but also provided detailed spectroscopic information about the composition of the disks.
Now, you've got a model of Spitzer right there with you in the room, right?
We do indeed.
So try to reorient things here so everyone can see that.
Let me point out some of the salient features.
Oh, that's incredible.
Okay, so this is the solar panel. And in our orbit, we're orbiting the sun, not the Earth, because we want to weigh the heat of the Earth. We always keep the solar panel oriented towards the sun. This piece down here is the spacecraft, which is a very expensive and highly reliable bus that points Spitzer around, issues commands, collects the data, and so forth. And this part up here is what we used to call the pointy end. Okay? And so this is the telescope. You can see it's a reflecting telescope, primary and the secondary. This chamber back here is the instrument chamber where the instruments sit. And then this section back here is a tub of liquid helium, which at launch contained enough liquid helium to keep the instruments cold. Now the telescope had to be cold as well. And the way we kept the telescope cold is sort of suggested by this black surface here. The back side of the telescope, the side away from the sun, was pointed into the deep, cold refrigeration of space. And that system lost heat to space by a process called radiative cooling. So we kept the telescope cold by radiative cooling, extracting the heat that leaked in rather than by cooling it directly with the cryogen. And because of that, when we ran out of the cryogen, which happened in 6 years after launch approximately, the telescope still stayed very cold. And this radiative cooling is what allowed us to continue to operate for about 10 years after cryogen was all evaporated in a so-called warm emission mode, where we warmed up to a sizzling 30 degrees above absolute zero. And still were able to do really interesting work at our shortest infrared wavelengths.
Absolutely incredible. Well, I don't want to take any more of your time up. I'm going to hold up a copy of your book again. But if people want to follow the mission, want to be able to follow the work, and there's still going to be tons of science. I know how this works. There'll be science coming out of Spitzer for decades. Where should they go?
They can go to our website, spitzer.caltech.edu. That's the simplest thing. And the book, which you're about to show, is published by called More Things in the Heavens, published by Princeton University Press, also available on Amazon.
Wonderful. Maybe you can move the camera back so we can say goodbye here.
Okay.
All right. Well, Michael and Peter, thank you so much for joining us today, and also thank you for watching over Spitzer, both in up to its creation and its operation for all of these years. I know I've been enjoying all of the science that's come from it, and it's been an absolute pleasure in talking to you both today.
Thank you very much, Fraser. Nice to meet you.
All right. Thank you so much.
Bye-bye.
Wow. That was so cool. All right, let's move on to the next portion of the show. So we'll go to Annie first. Annie, let's talk about the possible successor of Spitzer, the James Webb Space Telescope.
I like how you said possible successor, because oh boy, is this thing ever going to launch?
It's going to launch. It's going to launch.
Mm-hmm.
It can't not launch.
So I'll tell you when it's not going to launch.
Yeah.
It's not. And this was published, I think it was January 31st, the GAO, that's the Government Accountability Office, annual report on James Webb Space Telescope, subtitled, Technical Challenges Have Caused Schedule Strain and May Increase Costs. Yeah, such a fancy title.
Yeah.
Anyway, this thing is not going to launch in March of 2011, 2021.
Yeah.
I'm sorry.
Yeah, 2011 is 10 years ago. Yeah.
Well, sometimes it just feels like a thing. Anyways, it's not going to It's not going to launch.
It was originally, I believe, expected to launch in 2011. I think that's where that got into your head.
I don't even know what it was originally supposed to launch anymore. I really don't.
Yeah, 2010. You know what? Honestly, I'm like out of jokes about James Webb at this point. Like I'm done. I don't even need to make any jokes anymore. The jokes just write themselves. So
I didn't understand Dr. Pym.
It'll be powered by fusion.
What's that? It'll be powered by fusion?
I said by the time it launches, we'll have tabletop fusion. We'll just power it that way.
Well,
Yeah, but it won't be powered by tabletop fusion because the technology won't be mature enough, because that's actually a thing in some of the reports is the technology maturity level. Not joking.
the joke I've heard is that it will be, by the time it launches, it will be far enough ahead in time it'll be able to watch its own launch. Anyway,
Yeah.
hit us with the news, Annie.
All right, so 12% confidence level for launching in March. NASA operates on a 75% confidence level, and that's not until July 2021.
Right.
However, integration is not complete yet. Not all of the spacecraft parts are put together, and all of these parts have to be tested separately, because guess what? There's no facility in America big enough to test this entire thing as a unit at once.
Right. There's no great big vacuum chamber that you can take the thing, put it inside, expose it to all of the parts of space, let it unfold, fold back up.
It's just too big.
Yeah.
We have big vacuum chamber. There's one here in Ohio. There's a huge vacuum chamber here in Ohio. It's not big enough. It's just not big enough. This telescope is huge. So yeah, all these parts have to be tested, and it's not done integrating it. There's 501 faulty bolts, and they don't know which ones they have to replace yet.
Well, hold
because
on.
They have to do more testing. Yeah, faulty. They're literally not strong enough. They were found deficient in another project by the contractor, and the contractor that's building this is Northrop Grumman. I wasn't able to find out which other project they were found deficient in. And I'm assuming that they were found deficient in that project. And then, by the way, it wasn't good enough for this other project. It's not good enough for the space telescope. But rather than just tear the whole thing apart, put new bolts in, and reassemble it, they're like, we're going to do some testing to see which of the 501 bolts need to be replaced.
Right.
That's not even to touch upon the fact that there's 181 actuators. Mm-hmm. And I'm assuming each one of those 181 actuators is considered a single point of failure. But there's 300 single points of failure. And that means that there are 300 places in this telescope where if one thing goes wrong, it's just dead in the water. Mm-hmm. It can't do any science.
Yep.
Yeah.
So, we saw NASA go through this process where they evaluated Northrop Grumman's work about 3 years ago or so, and they went through Northrop Grumman's work with a fine-tooth comb and found that the original date that had been proposed was not realistic. And so they went and revised the schedule. And generally, NASA is really good at this kind of work. They are project management specialists. They've written many of the books on project management. And so I felt pretty confident at the new estimates that they were proposing. But I got a chance to interview Paul Geithner several months ago for my channel, and we could definitely get the sense that there was some slack that had been in the time frame that has come together a little more. But come on, right? March, April, May, June, July, 4 months. We've been waiting 20 years. Is 4 months that bad?
Compared to some of the other timelines, no, it's not that bad.
So,
my fear is that they're going to find more problems, because the part of the report said, yes, you are going to find more problems. They are going to take more time to fix. These things will delay even more. And there is a thing called a schedule reserve where, there's considered slack in the timeline, but it's been used up by unforeseen problems, like installing a panel upside down, quality assurance checks that just haven't gone right. And there's still some pushback from, even though this report says, look, you're not launching in March, NASA's like, or the project, I can't quite remember which, is like, we'll reassess everything in the spring and we'll announce a new launch date then.
Yeah.
It's not launching in the spring.
And of course, with additional time comes additional cost, right? The budget has to go up.
Right, because you have all of these people that are being held on contract way longer than anybody thought. So that's where the skyrocketing costs are coming from, is literally from labor, because this is just taking so long. Yeah, it's...
Well, here's hoping that that 12% or whatever that number is increases to back to 75%, that they find all these problems, they go away, spacecraft gets put on a boat, sent to Kourou, French Guiana, gets loaded onto an Ariane 5 rocket, and off it goes to space, and there are no problems.
That's the other thing. They have to design a new fairing, or they're in the process of designing a new fairing for the Ariane 5 that's vented to reduce stress on the sun membrane for all of this. And that's going to be tested later this year, I think.
Right.
So that's on track. But yeah, everything else it's going to take some time. I wouldn't put money on a March launch.
No, I wouldn't put money on a March. No, a July launch sounds okay. If it has to be a March 2022 launch, that also sounds fine. I just want this telescope to fly. At this point, just do it right. As you said, hundreds of points of failure. Please just fly. Just fly and be safe. That's what I want. So,
yes.
All right. Well, keep us posted, Annie.
Will do.
Brian Koberlein, I believe half of the time I introduce you here on the show, it is that Einstein was right. Was Einstein right?
Einstein was right.
Right on. Again. How was Einstein right this time?
So this is actually a really interesting study that looks at a thing in general relativity called frame dragging. And most of you will know that in general relativity, when you have a large mass, gravity is actually an effect of warped space. So mass warps space around it, and that causes things to move not in a straight line that we think looks like a force of gravity. So that's exactly what Newton says was a force, Einstein says with space-time. But one of the things in relativity is that if a mass is rotating, then it actually drags a bit of the space with it as it rotates. And that means that space around this rotating mass is twisted. So if you have this rotating black hole, for example, it's rotating around, and you were to drop something into the black hole, it wouldn't fall straight to the black hole.
Right.
It would actually fall in and then twist around while it was falling. And that motion effect is not because the particle is moving, but because space is moving.
Okay. So let me see if I understand this correctly. So you've got this situation where I'm sort of imagining like when you have like those some kind of spinning thing that you drop, like some drops of paint or something on it. It forms a circle, right? That in fact, from the perspective of the thing falling into the black hole, does it perceive it as a straight line, like that you're just falling straight into the black hole?
It perceives that it's in free fall.
That it's in free fall.
Let go of it, and it just feels like it's just falling
you're
to
just
the black hole.
Falling. But from the perspective of an outside observer, you're seeing this thing go into orbit and sort of spiral inward until it disappears beyond the event horizon.
Right. So it rotates, it orbits around before it falls in.
And that's because space-time itself is being just torqued around in a circle around the black hole. Unbelievable. Yes. Okay. Yes. So, or so Einstein believed.
So Einstein believed. Now, in 2015, we actually measured this effect. So we actually did it in a space probe that was orbiting Earth called Gravity Probe B. And for that, what they did was they had basically the most spherical object they could make and put it into space and let it orbit around the Earth while it was spinning. So you take this almost perfect sphere and you spin it, and then you let it orbit the Earth. Now, according to Newton, since it's a perfect sphere, there's no torque on this object. So since it's just falling around the Earth, its rotational direction should stay exactly the same. But if there's frame dragging, then what happens is basically there's more frame dragging closer to the Earth than there is a little bit farther away from the Earth. So this sphere is in this twisted space that's trying to twist it.
Right.
And so what happens is that sphere would change direction slightly. It's
would
called
precess.
lens steering precession.
Right.
And so it would rotate and kind of precess like a top. And that's exactly what this sphere did. And so they put this thing in space with gravity probe B, and they watched it, and it actually did precess exactly like Einstein predicted. So that is the experiment that showed Einstein is definitely right. So that the whole frame dragging effect, there was no question about whether or not that was true. Here's where it's interesting. We had to build a very special spacecraft and put it in orbit around Earth just to measure frame dragging around Earth. You have to have some type of probe in order to see this frame dragging. So the idea that we could measure it anywhere else, well, we'd have to put a space probe there, right? So there's no way we can do this, except with radio astronomy and pulsars, you can. So in 1999, there was this binary system that was discovered, and it was a white dwarf and a neutron star, which is a pulsar. So we can see radio pulses coming from this thing. And these two objects are about the distance, the diameter of the sun away from each other. And they orbit each other about every 5 hours. So what happens is the white dwarf is spinning and the pulsar is going off. And because the white dwarf is spinning, it's undergoing frame dragging. There's frame dragging around the white dwarf. And that means that the orbit of the neutron star is being precessed slightly. So it's kind of like, there's your probe to do this. So what they did is they watched this pulsar over 20 years. And because pulsars are very precise pulses of radio light, you can measure the orbit of the neutron star really, really accurately. So they watched this over 20 years and they saw the orbit of the neutron star precess because of frame dragging. And it was exactly as you would see with Einstein. So we've got frame dragging now right near the Earth and 12,000 light years away. But what's cool about the result is that because of the frame dragging, they can measure how fast the white dwarf is spinning. They know how fast the neutron star is spinning.
Right, because it's a pulsar.
Measure how fast
blasting
the
out
white dwarf
radio
is spinning.
waves.
And it rotates once every 100 seconds, which is actually really fast. And what that means is that it must have been sped up. A white dwarf wouldn't speed up by itself. So it was sped up by the material from the neutron star when it was a star.
So the white dwarf,
as that star was dying, some of that was captured by the white dwarf, speeding it up. Then that star went supernova, leaving a neutron star.
but wouldn't the star that created the neutron star die first? Because it would be a bigger, more massive, more short-lived star, right? So wouldn't that be the one that dies first, and so the other one would have been a main sequence star?
Not necessarily, because you can have an older star that's captured a younger star. You can have one that's formed and then another one formed later.
Right. Okay.
So this idea of how these supernovas are affected is exactly what you can get.
Right.
So it's really kind of cool.
Yeah, it's really incredible. I mean, is this the beginning of a new kind of astronomy? I mean, do we need a very special circumstance to be able to make these kinds of measurements, or could we get to a point where really any kind of binary companion around a neutron star might help us get at this?
I think you have to have the right type of binary star. I think what this is really demonstrating is that a lot of these fields of astronomy, such as radio astronomy, are getting so data-driven and so precise that we can now do experiments we would have never thought about before. The idea of monitoring these things with precision over 20 years is a massive amount of data. We can do that now. We have enough radio telescopes to gather that type of data over long periods of time. And as more of these radio telescopes come online, we're going to be able to do more sophisticated observations and find these special types of binary systems and stuff.
Absolutely incredible. Wonderful. All right, Chris, what do you got for us?
Well, so I think I actually have a more upbeat and happy story, I guess, after the dismal state of the James Webb Telescope. And so last week was actually a very historic day for astronomers who are interested in the sun, because we got the first light images from the National Science Foundation's newest solar observatory, and that is the Daniel K. Inouye telescope. I hope I'm pronouncing that right. And so you get this beautiful image this is from their first light back in December. And if you could just zoom in a little bit more, so you can really see the features.
I don't know if yeah.
That's
the animation.
Right. We can get to that one later. But if you look at the static photo.
Yeah, I don't know if they're going to let me show it zoomed up.
I think that's good.
Yeah. No, that's as much detail as they can handle on the internet.
And so what you're looking at now is the most highest resolution image ever taken of the sun's surface. And there's just so much detail here just to unravel. Like, so the smallest features that you're seeing on this image, this telescope was able to reach resolution sizes on the scale of 15 miles, which is about the size of my current living situation here in Manhattan.
Right.
And so which is just phenomenal to think that you would reach that level of detail, which is about 5 times better than anything that's ever been done before with these solar observatories.
Yeah, I mean, these blobs that people are seeing on the screen right now, these are like the size of Texas, but that's not each one of these convective cells are like the size of Texas, but that's not the resolution. As you say, the resolution is just on the 20-kilometer range, which is just mind-bending to think that we are seeing the sun 150 million kilometers away from us.
Yeah, the granules are fantastic, but it's really about those fine details that's, I think, is really making us excited, because we've never been able to see any star's surface with this much immaculate detail, and we're really taking advantage of having this main sequence star so close to us that we can actually learn something pivotal about main sequence stars. And so we can also look at the GIF image that you had up.
Yeah, okay, hold on 1 second here. I'll bring that back, and I'll let you see what we're seeing. Okay, so this is the one I think you wanted to show, the close-up version.
Yes, and this one's great because it has the scale replica of Texas, and you really get to see I guess that direct comparison between the size of these cells on the surface and between the great state of Texas.
And then this is the animation.
Yes, and don't stare at this for too long, because I feel that
you'll go crazy. Yeah, you'll go mad or
like
nauseous.
I lose my sense of time and space every time I stare into this image.
It's so beautiful. Yeah.
Yeah, it's completely mesmerizing, and I think the really just astounding thing about this is really just a manifestation of very basic physics of heat transfer through convection, because these granules that you're seeing are actually the tops of these tall, scorching towers that actually reach tens of thousands of miles down into the sun's depths. And so the bottoms of the towers are actually closer within the sun's depths get heated. And so as the hot plasma rises, the cold plasma lowers. And so you're actually seeing that through this time-lapse GIF. And I think the time scale over that GIF was around 10 minutes.
Oh, wow. So okay. That's 10 minutes of change on the sun.
Right. So you're really seeing that active process happening in real time there. And I think that's amazing. I mean, that we've developed that capacity.
What is we know this is a brand new, really powerful telescope that's been installed on Mauna Kea in Maui. What did it take to be able to produce images of the sun with this kind of incredible resolution?
So from what I understand, like this, they use this new mirror telescope that I think it has a diameter around 4 meters, and
right.
It's like this very sleek mirror that they have like these pistons attached to it and everything, and they have to keep it super cooled because if it's staring at the sun all day, it's going to heat up. And so they keep it like they keep it cool. It's like constantly being monitored for its temperature because if you heat up the mirror, it can cause distortions, which affect the resolution of your image. And so they're constantly adjusting the mirror to make sure it gets these pristine images. And I was reading that it can make up to 2,000 adjustments per second to
the temperature or to the shape of the mirror, like
with the shape of the mirror
with its adaptive optics.
Yeah, exactly. Yeah, it's some of the best adaptive optics technology like ever put to a telescope.
And you can just imagine, I mean, just the kinds of temperatures that are going, like, you're taking the sun, you're taking a 4-meter telescope, you are concentrating it down to be able to look at it, and that's just going to be heating up your entire telescope. And exactly. Temperature changes with telescopes are the devil, right? And so apparently they make ice at night on the observatory. So it has a big ice maker inside of it, and they work all night to make ice, and then they run this ice. They use this ice to run coolant through the entire observatory during the day to counteract the enormous temperatures that are being generated. Okay, so we've got these incredible pictures of the sun. What's it good for?
That's
Why?
A good question. And so the main purpose of this observatory was to try to get more precise measurements of the sun's magnetic field, and also to get a better understanding of the sun's corona. And so the corona is the uppermost layer of the sun's atmosphere, and it's this very diffuse, I guess, gas that can actually reach temperatures of millions of degrees. And you can actually see the corona visibly, like during times of a solar eclipse, because as the moon passes in front of the sun, that diffuse light becomes a lot more present. And it's a big mystery in solar physics as to why the corona, as diffuse as it is, can still reach temperatures of like millions of degrees. And that's believed to be connected to the magnetic field strength of the sun. And so I think one of the main priorities of this new telescope is to try to get a better understanding of the sun's magnetic field.
Right. And of course, this does have implications for us here on Earth, because we know that the sun can release these large flares our way. We can get all kinds of solar activity. It can be as nice as the auroras that we see, and as devastating as events that can disrupt our electronics, take our satellites offline, and potentially for astronauts that are flying out in space, they could be hit at the wrong time. They could be hit by a solar storm that will give them a lethal dose of radiation in just a couple of hours. So the hope is to get more advance notice.
I think that's one of those things you can learn by having a better understanding of the sun's magnetic field, because as far as I understand, the solar flares sort of trace the field lines of the magnetic field, and when the magnetic fields, I think when they reverse or break or something, it causes the dispersion of these highly energetic particles, which are responsible for a lot of the potential problems for extra sort of like low Earth orbit and things of that nature. And so this not only has a great bounty for the science, but also as a technology.
Arjone is asking in the chat, is the mirror covered in dark glass so the image is not overexposed? So here, like with solar telescopes, when you use a solar telescope, you block the light before it gets into your telescope. Do you know how they're managing the light so that it doesn't just like fire a laser beam inside the observatory and cut a hole out of the side of the telescope based on focusing the light of the sun?
I'm not sure, actually.
Well, I'll jump in then. So the telescope is an off-axis telescope. So unlike a regular refracting telescope where that you put the secondary mirror sort of sits in the middle of the telescope and bounces off of that, this is an off-axis, so the telescope is pointing at the sun, and then the light is coming off and kind of bouncing sideways, and it's going into an instrument, the secondary mirror, and in between the main mirror and the secondary mirror, there's this metal donut that blocks almost all the light that's coming from the sun. It's got this tiny little pinprick right in the middle that actually lets a fraction of the light through, and then that's what they're studying. And I forget what they call it, but it looks like a cooled metal donut that has this tiny little pinprick that they can actually let the light through. And this kind of relates to the fact that we're going to be seeing the European Space Agency's solar orbiter spacecraft flying to space on Sunday, which is going to get to a position to be able to watch the sun, to be able to eventually be able to see the poles of the sun from like within the orbit of Mercury. And then this joins the Parker Solar Probe, which has already been launched and is working to see the sun closer and closer. So we're going to get to this point where we're going to be able to see the sun from up close from Parker Solar Probe. We're going to be able to see the poles, which are, the poles switch around, and we'll be able to see the work from, be able to see what it's doing from here on the sun. What do you think? I've heard it called that we're entering the golden age of solar astronomy. What do you think about that term?
I think it's lovely.
Yeah, sort of matches the color of the sun right now. The caramel corn.
The future is bright.
The future is bright. Well, Chris, you are on my screen right now. So if people want to find out what you're working on and sort of follow you after the fact, where can they go?
I would say right now you can follow me on Twitter at @TheRealCcar.
Yep, I just followed you.
Oh, I realized. I remember the notification I got during class. I was very excited.
Real C Car. There you go. Everybody follow him.
Yeah, and also if you're in the New York area, I'll be giving my first public lecture on February 21st, part of Columbia's outreach program. It's a great time to learn about astronomy, and I'll be talking about stellar migration in the Milky Way and how maybe one day stellar migration might actually save civilization.
Whoa.
So, be a good one.
Where, if people want to watch this, if they're in the New York area, where should they go? How can they watch it in person?
So, if you want to attend it in person, you would go to Pupin Hall on Columbia University. So just look up Pupin Hall on your Google app and you'll find it.
On February 21st.
Yes.
Awesome. That sounds great. Unfortunately, I am another country and continent away from there.
7 p.m. I should probably mention the time.
7 p.m. Perfect. Yeah. Just who, what, where, and why. Brian Koberlein, what are you working on? Where can people find out more?
I'm working on stuff for Universe Today at the moment. So I've got a new post up today. I'll have another one up tomorrow.
Yeah, I signed you a couple of stories this week.
That's right.
The stuff that's outside of my pay grade. So that's perfect. And although they're kind of related. So
yeah. So you can find me on Twitter at Brian Koberlein and on my website also at briankoberlein.com.
Perfect. Annie.
So Sunday on CosmoQuest's Twitch channel, I will be continuing working on the Vera Rubin Galaxy in Photoshop, colorizing it. And I guess this weekend there's a whole bunch of launches, and I'm going to do my best to stream as many as I can.
So you're going to stream the Solar Orbiter on Sunday?
That's the plan. Solar Orbiter. Let me see what else launches, because there's 2 launches on Sunday. Solar Orbiter and I think a resupply mission to the ISS. So.
And the astronauts come home tonight. I don't think I'll be streaming that because I like sleep. But that makes sense.
I can be found on Twitter at Binary Blaze.
And on Twitch.
And on Twitch as CosmoQuest X.
Right.
X is where the science is.
Perfect. Well, so for everyone knows, I just did a video on abort systems that came out yesterday. I just posted our new QA that's going to be coming out on Thursday. It's got a special guest answer from James Davenport, who has his own YouTube channel, and I absolutely plan to pull him into the fold of the various science communicators that we work with. And then I've got an episode on this incredible picture from of the sun, which is why I kind of had some of these facts in my head, Chris. And then we've got an episode on the solar orbiter, assuming that it launches on Sunday. Otherwise, I'm going to have to redo the episode over the weekend if there's another delay. But so we got lots of good stuff over on our YouTube channel, as well as all of the great stuff that's happening on Universe Today. Let's bring everybody back. There's everybody on my screen. Well, we've reached the end of our hour. I think that was one of the best groups of guests that we've had in a long time. That was absolutely incredible to be able to talk to the project director of the Spitzer Space Telescope, especially at this time. How wonderful! So, thank you to. I'm assuming it was Nancy who coordinated that, but whoever worked on that from the Weekly Space Hangout crew, really appreciate that. Thanks to all of the moderators, all of the people watching us, and of course, all of my co-hosts. And Chris, great job. Welcome aboard. We can't wait to see what you come up with next. And of course, hopefully people will actually attend your talk on who are watching this. So we'll get you the Weekly Space Hangout bump.
I know who to thank.
All right. Thanks, everybody. And we will see you all next week. Stop the stream.